Is it okay now? Okay. So I think last time I wrote wrong thing, so maybe I just correct it because I thought that I wrote this way, but it was not the case. So I think last time I wrote something like this. I don't know, maybe I have some index and then maybe what I wrote was something like this. But somehow I didn't really put these boundaries. I mean, sorry, this is. So I didn't put this boundary on when I wrote this. If you don't have this, then certainly it doesn't really make sense. So I forgot to put this boundary last time. So this is one thing. And second thing is about the comment on this Rodenbach C-graph result. And so what I mentioned was somehow that it implies certain C0 rigidity of Lagrangian submanifold. So what I said was something like if you have a sequence of closed embedded Lagrangian submanifold, converging to some closed embedded submanifold, and all of them have the same dimensions, namely dimension of base is just 1/2 of the dimension of the simplex manifold. And then S is also Lagrangian. So C0 limit of Lagrangian submanifold is Lagrangian. But this one is okay under certain assumptions. And what I can say is first, if Sn are all, okay, so Sn can be written as a phi n of some L, S1 say, so that phi n are all symplectic diffeomorphism. And then this is okay. So this one somehow use so-called displaced energy. Displaced energy of such Sn times, say, if necessary, I take a product with S1 in X cross, say, S2 is actually maybe this displaced energy is actually uniformly positive. I mean, does not depend, it is positive and does not depend on n because they are symplectic diffeomorphic. So then from here, actually, yeah, we can prove this because their result says that if you have a submanifold which is not Lagrangian and of half dimension, if it can be displaced by topological reason, and then you can immediately displace it by Hamiltonian diffeomorphism. So therefore, yeah, if you have this thing, uniform lower bound for the displaced energy, then it is okay. But without such a condition, probably, yeah, it is not so apparent to prove this. And in the paper by this Rodenbach-Sekraf, actually, they assume that pi 2 of this x of, say, Sn, right, is actually 0 or something. And in this case, actually, Sn cross S1 cannot be displaced under, not S1, but yeah, maybe I take this one is inside of, yeah, the argument is a little bit different, but anyway, yeah, in this condition, actually, you can actually show that this one is not displaceable. Or maybe the ambient manifold is, so, or this one is equal to R to N and omega standard. And in this case, they can also prove this. So yeah, it is not just a closed-embedded Lagrangian manifold, but probably we need some condition like this or like this. So if you are here and then displace energies uniformly vanish from below, but if pi 2 vanishes, actually displacement energy is actually infinity. So therefore, in this case, actually, yeah, this special case of this. But anyway, so this is just a remark from the last time. And today I want to continue the discussion from the last time. So last time, actually, I briefly remind you the construction of Novikov cohomology theory. And also, yeah, so this is Novikov complex and how we define it. Maybe I just briefly remind you what I said. So you have this, say, Riemannian manifold, maybe closed Riemannian manifold. And then take alpha, it is a closed one form. So that all zeros are non-degenerate. Namely, closed one form is certainly locally exact. So therefore, near the zero, you can take a function so that its exterior derivative is equal to this alpha. And then such a function, the zero corresponds to the non-degenerate critical point of that local primitive function. Okay? So this is a non-degeneracy. So locally, this alpha is written as d of f. And if alpha p is equal to 0, then this p is a critical point of this. And so therefore, you can consider its Morse index, right? So here I consider the mu of p, its index, is defined as a Morse index, namely the number of negative eigenvalues of the Hessian matrix of this F. Okay, so it doesn't depend on the choice of primitives certainly. So this, and then we also introduce a Novikov ring. It's a Novikov ring. Maybe better to start from covering space. Sorry. Maybe better to start from covering space. Okay. So I have alpha, so therefore I can integrate alpha over the loop, and then you get a homomorphism from here to here. Right? And then you consider certain covering space, M of bar, alpha. Maybe I denote by projection by P. Covering space corresponding to this kernel of this thing inside of this pi 1 of M. Okay? And then we have two things. Okay. So one is that I have a function f tilde on this m bar alpha to r, so that this df tilde is equal to p star of alpha. You pull back the form from here to here, and then it becomes exact. And secondly, yeah, we can have a certain Novikov ring. Namely, if I denote by gamma alpha, this is a covering transformation group of this covering. Then certainly this one is isomorphic to the pi 1 m module this kernel of this thing. And so because I take a quotient of this one by this one, I have a homomorphism. Maybe I also denote by alpha from this gamma alpha to r. So originally this integration of alpha depends defined on the pi 1 of m, but because this is a kernel, so therefore I have this homomorphism. Right? And so, okay, so we have this. And once you have this, we want to take certain completion of group ring. So R is just some ring, some algebra, and then so this is some ring, and then I consider R of gamma alpha. This is a group ring, right? With coefficient in R, and then so this one is certainly written as AI and maybe GI, and AI is in R, and GI is in this gamma alpha, right? And this is a finite sum, right? But if we have this homomorphism, somehow we can actually take certain completion of this one. So that is a Novikov ring, which I wrote last time. So this is lambda alpha. So this one is also written as sum of AI and GI, but maybe now this sum may be infinite sum, not necessarily finite sum. And AI is again this element in the ground ring, and GI is in this gamma alpha, and this unsatisfying the following conditions. So for any real number, if you consider the index I, so that AI is non-zero, and takes the value of this homomorphism, right? Integral of alpha of GI is less than C, okay? Then this number is finite. So this is what I wrote last time. And so what does it mean? What does this condition mean? This condition, right? Maybe later, maybe I don't want to keep writing this. So I just want to abbreviate this. So this condition, we may just write this integral of alpha of GI tends to plus infinity. From now on, I just write in this way. Namely, if you have infinite sum, then look at the value of this GI under this homomorphism. And then you have a sequence of real numbers. And then this must diverge. If it is finite sum, it's okay. We don't need any condition. But if there is infinite sum, then this is this. So finite sum certainly cannot go to infinity. But so I just write this way from now on. Okay, so this is the condition. And then next I want to say the following. So now I define this Novikov complex of alpha. Maybe depends on the metric G, but yeah, maybe depends on metric G. Sorry, G is a metric, and here is a group element. So it's a little bit confusing, but this is actually a metric one. So as a module, it is written as follows. So maybe this is Ci and Pi tilde and some I. And Ci is an element from this ring R, and Pi tilde is an element of P inverse of 0 of alpha, and this is equal to the critical points of this function f tilde, so that I assume the following. So f tilde of Pi tilde tends to plus infinity. So if it is a finite sum, I don't assume this. But if it is an infinite sum, then I just assume that this one going to infinity. So from now on, actually, I don't really write condition like this. I just keep writing in this way. But it doesn't really mean that we only consider infinite sum. Okay. And then next, I define the delta. This is a C and K. Sorry. And then if I want to write K here, and then I have to put mu of Pi tilde is equal to K. So the index I denote by this is equal to this. Yeah, because it doesn't matter which lift you take. Okay. Then I want to define this. And then what I said is the following. So take any point here, maybe P, and then I want to map it to the sum over these things. So the Q runs over the critical point of F tilde, so that this maybe Q P maybe tilde, okay? So tilde, and then Q tilde, and then this Q tilde is equal to K plus 1. And this has mu of P tilde is equal to K. And what does this mean? This is the following. So I consider M tilde of P tilde Q tilde. So this is a trajectory like this. So you have gamma, which is a path in the covering space M bar alpha, so that this is a gradient trajectory. So therefore you have gamma dot of tau is equal to the gradient of F tilde of gamma tau, and if you look at the limit as tau tends to plus minus infinity, then maybe minus infinity, and then this one is equal to P tilde. And if tau tends to plus infinity, it's going to Q tilde. So you take all of them. And then for any real number t, you can shift this trajectory by t. Namely, you can define the new parameterization of this gradient trajectory, say by gamma tau plus t or something, right? So you just shift the parameterization. So therefore, if endpoints are distinct, then this action is free. And so we may just modify this action R, and then we define this on MP tilde Q tilde. Later, I may discuss about the compactness of this, or maybe smoothness of this space later. Not in Novikov context, but maybe Floer context. And so if the index difference is 1, then this set can be finite, non-degenerate points. If this metric and this gradient satisfy certain condition, like a third smell type condition, then this one is, non-degenerate finite set. And then last time somebody asked me the sign of this. And maybe I also discuss it later in the flow context in some cases. So anyway, so we have some way to give sign here. But in order to give sign, we need some data. So I have here gradient trajectory, right? So like this, like a P tilde to Q tilde. Then at each critical point, we have, say, unstable manifold or stable manifold. Either is okay. So say you have here, you have unstable manifold. Here you have unstable manifold. And then, so unstable, in this case, maybe it sounds a little bit strange because, so in this case, unstable manifold of this flow is something starting from here, like this. So maybe W unstable Q tilde. And here we also have unstable manifold here, W of P tilde. And this flow line certainly lies on this because flow line, the gradient flow line is the intersection of unstable here and stable here. So therefore, it's the intersection of these two things. If they intersect transversely, then under certain assumption, this condition, we may say that this one is finite point. And now we consider some additional data about this. So I pick the orientation of unstable manifold at each 0 of alpha. So I consider such a thing downstairs. And then lift it to a unstable manifold on upstairs. So I use such data. And if you have such data, such orientation of unstable directions, then there is a way to give sign here. And so in this way, somehow you can have this. And then, then I come to this. Then I come to this. And this is also a consequence of more Snell type condition. And this one implies that delta square is equal to 0. So people may write the following picture, like you have one critical point P tilde, and you have another critical point Q tilde, and then you have so maybe say, okay, so maybe I put tilde here, but anyway, so index difference 2, mu Q tilde minus mu P tilde is equal to 2. Then you may consider some moduli space of such gradient trajectories. And if it is closed manifold, then it's okay. So you don't have any breaking. But it may somehow breaks into this sort of union of gradient trajectories. So it may just split like this, right? So maybe like this one, maybe R1 tilde. But because this one is now the moduli space, in this case, after this M of P tilde Q tilde is one dimensional. And if you look at if this is not compact, and then you look at the limit of this, then limit corresponds to such breaking of it, right? And then because one dimensional manifold is closed, namely with that boundary, or even number of endpoints. So if you have one, then you have another one somewhere, like this. So you start from here, and then look at this delta of P tilde. Then you have something like this R1 term, maybe plus minus 1 here. And then you have also another term coming from R2 tilde and so on. But you apply delta again, then this one gives you this Q. And these two effects, actually, I just write plus minus, very, very rough way, but they cancel if you look at the orientation carefully. So therefore they cancel, so therefore from here actually we can see that this is equal to 0. It happens for any. So this is the reason why we have this. So this is a kind of key fact for proving this property. Okay. And now I want to consider the case of Floer complex. So this one I can erase. But this one I want to keep. So therefore I just write this way. So here I have this boundary of m p q of mu q tilde, so q minus mu p is equal to 2 is a union of r with mu r equal to mu p plus 1. And then this actually split into something like this, right? And then from here we can show this. Okay? And then the picture is what I erased. So therefore I also write this like this. Maybe it just split into something and also split into something. Yeah, this way. So I just keep this. Okay. So now I consider Floer case. I'm still in the introduction part and gradually move on to the naive idea of Floer complex. So last time I also introduced a path space like P, L0, L1. And this space is the following. So I think you still remember this. Gamma is a path from 0,1 to x, so that the starting point lies in L0 and end point lies in L1. Right? Just consider, maybe space of smooth path or space of continuous path. But anyway, we don't really use it so much. But then I also introduce certain one form, maybe one form, which is closed one form. By the following formula. So I take gamma from this, and then take C from the tangent space of this path space. And then I want to assign some number to this C. So this gives you some sort of one form. And what we consider is something like this. Like this. And then we have a local primitive and so on. Right? So I discussed that locally you can find some function on the path space so that if you differentiate this function, then you get this alpha. Okay, so maybe I also keep it, but yeah, soon. Okay. And then, okay. Then I start talking about the covering space of this. With some properties. And I discussed one thing, and then I didn't discuss another thing. So first one is just so now I consider the pi 1 of this path space. Right? And then I have a homomorphism to real numbers. again, it's an integration of this alpha of things. So namely, maybe I should write it more precisely. So just I have W from S1 cross 0, 1 to X. And maybe I denote this parameter S and this parameter T. So that W of S0 lies in L0 and W of S1 lies in L1. So you have two Lagrangian manifolds like L0 and L1. I have a kind of cylinder which somehow like this, right? Something like this. And then, so here I have a loop. Loop is this. So loop is, so S goes to this W S dot. Right? So S is a parameter on circle, and if you fix S, it's a path from L0 to L1. So therefore, it gives you a loop in here. And then I just map it into the integration of omega over S1 plus L1. And because L0, L1 are Lagrangian manifolds, so omega vanishes completely both sides. So therefore, if you have a, deformation of such things, if you have a homotopic cylinders with these conditions, then the boundaries are always lie on the L0 and L1, and then you just use Stokes formula, but the part mapped to L0, L1, omega is 0, so therefore you can see that this is actually a homotopy invariant. Okay, so this is one. This is one. And so this is kind of ambiguity for the primitive function downstairs. But now I take a covering space correspond to the kernel of this. So now I take a kernel of this thing. Corresponding to pi 1 of this PL0, L1. Then certainly we can have a certain function on this covering space, so that the pullback of alpha is d of a L0, L1. Okay, so this is so pi star of alpha L0, L1 is equal to d of a of L0, L1. Okay, and then next thing is that in the case of Novikov complex, I put this condition here to give a grading of this complex. And what's the corresponding thing here? And that is something related to the Maslov index. And in this case, I don't know, maybe Maslov index or maybe Maslov-Viterbo index. And so I will also discuss such index, maybe later. So now I consider the pi inverse of L0 intersection L1 going to Z. Sorry. No, not yet. So sorry. Maybe I should write mu L0, L1 from pi 1 of P L0, L1 to Z. Sorry. So this is the Maslov index, which this one I discussed last time, right? So I have a surface with boundary, and if you have a simplex vector bundle, so that on the boundary, this simplex vector bundle contains certain Lagrangian subbundle, and then we can define its Maslov index. So this is the Maslov index, and so now if I have not only this, but also kernel of this. Sorry. Okay, so now I just remove this, and then just take intersection with the kernel of this. Okay, so in order to have this functional, this is enough. But because later I also want to discuss about the grading of this complex, I also need to discuss this. And so I take this, and then take its corresponding covering space. Certainly such a thing exists. So because of this, you have such a thing. And this is ambiguity for grading. So therefore, if I have this, so maybe I can just write this way. So because we consider covering correspond to this, so this one implies this. And because we have this, so from here we have, again, maybe I also denote by mu L0, L1, but maybe pi inverse of L0, L1 going to Z. So I will also discuss this later. So this one is a replacement of the Morse index in this setup. So I will tell you later. So anyway, so first I have these two things, and then we can just mimic this construction. Okay, I just mimic this construction. So maybe I just write it this way. So just compare this one with the following one. So now I have CF K of L1, L0, and this is the following. So this is the sum of CI and PI tilde. And sorry, maybe I should say one thing here. I didn't really say this. Okay, so I should say this. So here, this thing is the intersection of two Lagrangians, and I assumed L0 and L1 are transversal last time. So I assume this. So this is a finite many point in the manifold X. But now I consider it as a subset in the path space. Certainly you can think of it as a constant path. Right? This is a constant path starting from L0 to L1, and then it should be mapped to a mapped intersection point. So this is a constant path from L0 to L1. And if you look at this formula, if you want to have a 0 of one form, so if this is 0 for any xi, certainly I have to assume certain condition at the boundary, but anyway, for any xi, omega is non-degenerate. And xi is arbitrary vector field along the path. If this one is equal to 0 for any xi, then this gamma dot must be 0, right? So it's 0, and then this gamma dot t must be 0. So therefore, gamma must be a constant. So 0 set of alpha is nothing but constant path. And now I have a covering space like P0, L1 tilde to P0, L1. So here I have a subset of constant path, and then take its lift. So this is this set. Okay? So I just come back here, and then Ci is in this R as before, and this Pi tilde is in the same way. So pi inverse of 0 of alpha L0, L1, but this is same as pi inverse of L0 intersection L1. Okay? And then I assume, again, this condition. So I don't really write it so precise, but now you may understand what does it mean. So I just write it like this. And then finally, I have to assume this mu L0, L1 of this pi tilde is equal to k. Okay. Is it okay? So this is a Novikov complex, and this is Ci and same Ci, and pi tilde. Here it's a zero, the critical point of this primitive function, and this is also critical point of primitive function. And then if it is infinite sum, I assume this condition. This is exactly the same as this condition. And then we also put this grading condition. So this is a definition of this module. And we can define such a thing for any ring R, right? Just a module. And then next we want to define this CF K2 CF K plus 1, and then ask whether it satisfies this property or not. Okay, maybe I come back to this. So this is the covering space. Okay. I think this is already okay. And also we can discuss the Novikov ring. So now we have the Novikov ring. So here, I still have something here. So gamma alpha, and then from here I consider R of gamma alpha, and then from here I define this lambda alpha. So I define covering solution group, and then this way. Yeah. So here we also consider same thing. So we have this pi1 of path space of A01, and then moved out by this kernel of integration of alpha A01, and intersection with kernel of mu of F01. So I denote it by gamma. It's a group, abelian group. And then I consider its group ring. And then from here, we take a completion with respect to this integration of alpha L0, L1 things. So namely, I have this lambda. This is the following. So I have a sum of AI, and so GI is not so nice, but anyway, GI. And now AI is in R, and GI is in this gamma, so that if we have infinite many terms, and then we assume that integral of this alpha L0, L1 over this GI tends to infinity. Okay. So I define this homomorphism, right? So I have a loop, and then I take the value, and then this. And this one is a graded ring. Because grading comes from this element. Yeah. So graded ring is coming from this mu L0, L1 of this GI. So it is integrally graded ring.
In the definition of gamma, why do you have intersection of those kernels?
Pardon? So I take this intersection, yes?
No, I thought it should be a bigger subgroup.
So this one, actually, you have a pi1, right?
Yeah.
And then it's a kernel of this and kernel of that, right? They are normal subgroups because the target is real numbers. So then you take this intersection that is also, or maybe this is actually normal subgroup, so therefore it is actually group, right?
I just thought that you should.
No, I think if later I can also say the following. This one can be embedded into certain universal Novikov ring. Or maybe, so this one. Namely, I have a homomorphism from here to this. Right? And this is actually injective. Okay? You can have some element here, then consider the image by this homomorphism to get this homomorphism to get this. Then if it is 0, then it belongs to this. So therefore, this group is actually embedded in these things, right? So maybe at the beginning, probably you don't really like this, but I explain this covering space. Then you have a covering transformation group. And then this covering transformation group is certainly this one, right? Maybe later, maybe I can tell you a bit more different way. But anyway, so this way. So this is the Novikov ring, which is analogous to the Novikov ring we have. And maybe I can just tell you this universal Novikov ring stuff. So here, actually, for our purpose, actually, it is on, I have to consider the grounding R is maybe rational numbers or maybe real number, complex numbers. But at this moment, I can consider any ring to define this universal Novikov ring. So this is actually defines the following. So sum of AI and E of mu I and T of lambda I. So I consider such a thing. So E and T are both formal variables. So E may be confusing, but for some reason we pick E. So therefore, this is not the usual E, but just. So anyway, so we consider this, and then AI are just element here, and mu I may be just integer, and lambda I real number, so that if there are infinite many terms, I assume the lambda I tends to plus infinity. Okay? So we have such a thing. And this one is somehow corresponding to this guy. So this ring actually canonically embedded in this ring, right? Just you have some element gi, then first define this lambda I as the integral of gi, integral of alpha over gi, and then you get lambda I. And for mu I, you take a value of this mu L0, L1, and then you get this. So in fact, this one can be embedded like this. Here. And for later purpose, maybe I just also introduce lambda 0. Maybe here I may have lambda nov or something, because later I consider different lambda in the Tori case. So lambda nov 0 is the same condition, but now also lambda I is non-negative. And if I write lambda nov plus, and then the same thing, but here all the exponent of t is strictly positive. So this one contains this, and this one contains this. I may use this later, but today probably I don't. So there is such a universal Novikov ring, which actually contain these geometric ones. But anyway, so today I just consider this. So then, if you look at this is actually a lambda. This is lambda, right? This is lambda. Maybe I write lambda L0, L1, say lambda L0, L1. Lambda here. So this is lambda L0, L1 module. Because this is a group, some kind of completion group ring, right? And then for each group element acts by covering transformation on these PIs. So then if you have a finite linear combination, certainly such a thing acts on it. And if you consider infinite sum, then because of this condition, the image also satisfies this condition. Maybe it's not so hard to see. So therefore, it is actually lambda 0, 1, lambda 0, L0, L1 module. And also, if they intersect transversely, then downstairs in X, yeah, L0 and L1 intersect only finite many points. And this is actually a free module generated by those intersection points over this. So this is somehow what I wrote last time. I mean, last time I think I wrote something like this, right? Always I may write this kind of free module generated by the, say in this case, intersection point or something. Maybe last time I wrote this kind of thing. Well, maybe the Novikov case, I consider free module generated by the zero of one forms. And why this? So here I have this P L0 L1 tilde, and here I have pi, and here I have P L0 L1. And then I take the intersection point here as a constant path. I have P here, right? And then here, I pick one lift. Yeah, just pick one lift. And then other lifts are related by covering transformations, right? Then other lifts of P are equal to some G times P, so that G is in this covering function group, right? So here I take the linear combination of points here, but this one is a orbit under this gamma action, union of orbit or gamma action through such a lift. Yeah? So you pick one lift for each intersection point, and then everything is actually obtained as a union of those things. So therefore, you can see that this is actually a free lambda 0 lambda 1 module. So here actually free module means free module over lambda L0 L1. And Novikov case actually free module over the Novikov ring of the one form. Over this. So anyway, so this. And so this way, I have a module over this Novikov ring, and then next I want to consider this. Okay, but last time actually what I said is some gradient flow line, flow trajectory of this A L0 L1 is something to do with this. So that R times 0 is mapped to L0, and R times 1 is mapped to L1, and satisfying the following condition, like a du d tau plus ju of du dt is equal to 0. But here, what gradient means? So we need some metric, right? So usually we need some metric, and this metric is I wrote like a formal L2 metric, right? Coming from this Gj. Maybe I also remind you what it was. So maybe now I just change this. Yeah, I don't need this anymore. So I just erase it. Okay. So this is something like this. So I have C1 and C2 as tangent space of this P, and then we want to define some L2 type metric by this. And so I pick j at the beginning. So I have x omega and then pick one j. Sorry, maybe I should say this. So j is j omega from the last time. And then I have a metric gj on the manifold x. And then using this gj, you can define this kind of formal L2, L2 inner product. And you do some formal computation. And then the gradient flow trajectory of this function now, using this formal L2 metric, is actually correspond to this equation. So J harmonic curve equation. So this is the equation. Right? So now now we consider the corresponding question like moduli space this. So this is a moduli of Floer trajectories. From P tilde minus to P tilde plus. I denoted by P tilde minus and P tilde plus. Certainly this one depends on the boundary condition, so therefore L0, L1. And also this choice of J. So maybe I just pick, keep such data here. But later I just write it just M tilde of P tilde minus and P tilde plus. Okay? But it depends on those data. Sorry, this is not a moduli. It's a space. It's a space. The space of Floer trajectory from P tilde minus to P tilde plus. Sorry. So this one consists of the following. So this one consists of the following. So you have a U from R cross 01 to X with three properties. One is each one is J holomorphic map. And second one, it satisfies boundary condition. And third one is actually a asymptotic condition. And so J holomorphic condition is actually this one. So maybe I just write it again. So J holomorphicity is nothing but this du d tau plus ju du dt is equal to 0. This is a holomorphic equation. And then boundary condition is this u r times I lies in this Li for I equal to 0, 1. And then the asymptotic condition is, maybe I just write this way. But what does it mean? Right? Because U is a map to X, and P tilde is a map, P is an element here. So what does it mean? So this is the following. So the last one, so the last condition, I just write this way later, but this one means the following. So first of all, I have a limit of this u tau t in p plus minus. So this is element in X, right? Maybe element in L0 intersection L1. Okay. And so now I consider this u as a path. So now I consider it's a path from real line to this, so to this P L0 L1. Okay. I don't know what is a good way to write it. Maybe I just write L of u or something. Okay. So some curve in the path space, right? So what I have is here R going to this PL0 L1. Here I have this L of u. Yes. But here we have a covering like pi coming from PL0 L1 tilde. Right? And so now I pick P tilde minus. So here I have this P plus and P minus. Right? And then I pick one lift like a p tilde minus. And then try to lift this curve Lu to the covering space so that initial point is this p tilde minus. So lift this Lu to p tilde L0, L1 so that with the initial point equal to p tilde minus. And then you get some end point, and then the end point of this lift is equal to p tilde plus. Then we call this limit of u tau tends to plus infinity is actually p tilde plus minus. So this is not really precise way to put it. I may say that this Lu has a lift which start from p minus tilde and end at p tilde plus. Right? You have a path downstairs and then you lift it. And then these two, p minus and p tilde plus. Yeah? So if this Lu has such a property, and then we call this one has this asymptotic property. So here I put this p tilde minus and p tilde plus by this. So what is good for these things? So this action function now, or this A, L0, L1, is defined on the covering space here. And this one controls so-called energy of the solution U. So let's suppose U is a solution, this M tilde or P tilde minus and P tilde plus. Certainly I need a bit more data, but I just abbreviate it like this. And then we define this energy. Maybe people may write this. Yeah, so I just integrate over R cross 01. So this is the energy for the mapping. And if this is J holomorphic, this is equal to just integral of this term, because these two terms, the normals are equal. And so this one, we define it this way. So this is the energy of the map. And we can show that this energy is the difference of values at p tilde plus and p tilde minus. Okay. So this is simply because the following. So you certainly you can do the same thing for most case or Novikov case, but this one is the following. So okay. So maybe it's easier to consider most case. So therefore most case. And then you can literally translate into this. Okay, so if you have a M and G, and then you have a map like this, and then take a trajectory gamma from R to M so that gamma dot is equal to the gradient of gamma, right? And then you now we consider integral of this gamma dot square of d tau, right? But this one is equal to the gamma dot and gamma dot, but gamma dot is equal to gradient of gamma d tau from here. And then this one is nothing but d tau of f of gamma term, right?
Gradient F.
Ah, sorry. Thank you. Gradient F. Thank you very much. Gradient F of gamma. So therefore, if you just integrate it, and if you have endpoints, and then this is actually F of gamma plus infinity minus F of gamma minus infinity. So you have a trajectory starting from some critical point to another critical point, and then this value is equal to the difference of these two things. And in our case, actually our equation is somehow du d tau is equal to the gradient of this A of L0, L1 of this U of something. Because if I compute this, it's actually minus J of du dt. Tau something, right? Okay. So therefore, if you look at this is nothing but the holomorphic equation, right? So holomorphic equation can be written as a gradient trajectories. So here, instead of this gamma, you consider this thing, but this thing over 0, 1 things. So therefore, you have to integrate all to 0, 1. But then you just do the same computation, then you end up with this. So this is just a computation. So as I said, we don't really use this covering space so much, but sometimes it is really, If you have this picture, then you can just mimic some argument from finite dimension argument. Okay, so this. So if you fix these two endpoints on the lift, and then the energy is actually controlled by the endpoint, so therefore it is constant. So now something which I may discuss later. So I just write some property from here. So this is the somehow compactness or lack of compactness of this M of P tilde minus and P tilde plus. So this is again the quotient of this M tilde, P tilde minus, P tilde plus by this shift action. Yeah? So here I only take this thing, but I just shift the permutation in tau direction, right? Instead of tau, I consider tau plus capital T, and then this is action. So this is way. And second thing is some sort of transversality of these things. And yes. So if you pick certain J, or maybe part out some data like a J or L0, L1, something, and then can you make it a manifold? And so this is actually coming from certain Fredholm setup. And if possible, you can use some third-Smell theorem. Or maybe, in general, we have to use abstract perturbation theory. So in order to achieve this, somehow we need something like this. So then maybe I have to say it a bit more carefully, but if it is a manifold, then you can consider its dimension. Now this dimension is controlled. Now, energy was controlled by this function A, but the dimension of this one is controlled by this index. So mu p tilde plus minus mu p tilde minus -1 because I just take a quotient by r. So we may have these things. So in general, yeah, it may not be transversal, but still we can talk about its expected dimension or virtual dimension as the index of certain linearized operator, and then that is given by this. So, okay. Certainly, yeah, for this space, we have a bound for energy, and it can be really used to discuss compactness and so on. But as you know, so now our space is non-compact, like yeah, this R cross interval, right? So therefore, as in the case of gradient trajectories, it may split into several trajectories. So it may split several trajectories, right? So this actually can be decomposed in this way. So here I have just map U here, but maybe I have a bunch of maps to go there. And also, in general, although the energy is bounded, you may have so-called bubbling of phenomena. So you may have some point here, and then you may have some sphere bubble here, and so on. I don't know. Or maybe you may have a disk bubble on the boundary. I don't know, maybe somewhere here. So this is so-called sphere bubble. And this is a disk bubble. So this is what I said, this lack of compactness. It may not be compact. Firstly, it may split into several trajectories. And also, some derivative may diverge somewhere. And then, roughly speaking, such a thing happening in the interior, then you may have this sort of sphere bubble. And if the derivative blow up close to the boundary, and the point is getting so quickly to the boundary, or maybe the derivative diverges at boundary point, and then you may have this disk bubble. So in general, you may have this. Okay. So maybe I discuss such a thing later, but let's suppose that this pi2 of this x Li is equal to 0. So this is a condition what Floer actually first considered. And in this case, certainly this one implies pi2 itself is also trivial, right? And so if we have any spherical map, anything like F, and then certainly you integrate it over here, it is equal to 0, right? But if we have such a sphere bubble, it's a holomorphic sphere bubble. And holomorphic map, I may discuss last time, actually this integral is nothing but the energy of that. And so it is non-constant, then it must have positive energy. So therefore, under this condition, you don't have such things. So under this condition, you don't have these things. Okay? And similarly, in this case, you have a map like D, boundary D, going to X and Li, any map W. Then certainly this W, the pullback omega over W over the disk is certainly 0, right? Because of this. But if you have such a holomorphic disk bubble, then this is, if it is non-constant, yeah, if it is non-constant bubble, and then certainly this area, simple area, the energy, it must be positive. So therefore, under this condition, actually you don't have these two possibilities. And you can only worry about this kind of splitting the trajectory into several things. And then that is exactly same as this. And I may have to say a bit more about this, because here I say that it may split in several pieces, not only these 2 pieces. But if this one is 2, right? And then if you split several pieces, and if you also use this kind of formula, then you can see that one of the components must have negative dimensions. So if you have transversality, the negative dimension thing should be empty. So therefore, you can only have this kind of splitting. Okay? So this is a story for this. And then I also want to discuss what Yonggen-Oh observed briefly. So in his case, actually, he considers monotone Lagrangian manifold. And also the minimal Maslow number is at least 3. So actually, he assumed a bit more condition, but anyway, this is the key to avoid these 2 things. So why is this the case? So let's suppose that such a thing happening, right? So let's suppose that for simplicity, you have just one sphere bubble like this. So here I have this P minus and this P plus, right? Okay. And so, okay. And then let's suppose this homology class A. This is representing homology class A. And then you consider the space like this. Originally we have this thing. Maybe here it's converging to P minus and converging to P plus. And in the element of M, P tilde minus and P tilde plus. Okay? So this is just a geometrically P minus P plus. But this tilde is, I already erased, but yeah, so anyway, this. And then this one is a union of the 2 things. So this is the union of this one and yellow one, right? Yellow one. And one can show, actually, yeah, this we need, say, yeah, some monotonicity formula argument or something that actually they must meet because you don't have so thin solutions. So therefore, they must meet. That means you have a moduli of a sphere with one mark point like this, and you have another moduli floater like this, and they must meet, right? So we have to do this. So now I consider this M of sphere of A. So this is actually the map like this. So this one is something like this. This one is equal to the map like F from CP1 to X and J holomorphic, and representing class A. So F star of CP1 is equal to A. Okay? And then I put one marked point because I want to consider this point, one marked point. So therefore I need one more thing. Here I take one marked point here. Okay? And then modeled by the automorphism of P1. So this is actually again Fredholm's theory. We have a Fredholm setup, and we may have some transversality argument and so on. And this expected dimension of this is equal to the following. So now I consider the real dimension of this moduli space, and then the ambient space is dimension 2n. And then I have a Chern class, first Chern class of the ambient manifold Tx divided by A. So this is an index of the Cauchy-Riemann operator on CP1 with coefficient in the pullback bundle of the target manifold. And then I have a point here. So the point is actually real two-dimensional freedom. And then this automorphism certainly PSL to C. So therefore this is minus 6. Right? So therefore this one is 2n plus C1 TXA minus 4. So this is one. And for this one, okay, so this one is A. So this one is A, so this one A. And how about this? And geometrically, the end points are P minus P plus. So therefore, I may say that here I start from P minus tilde. Okay? Just lift it. Then I start from P tilde, P minus tilde. And then the end point is not necessarily this P tilde plus, but maybe different things. Right? Because what I consider is a lift of the path. And then roughly I'm considering the following way. So maybe it's not so easy to see if green is good or not. But anyway, so I have a path like this, right? So here I only consider this. But here it's like this. But somehow here actually suddenly I have to travel over all of this, right? And all of this. I mean, how to say? Maybe this picture is not so easy to see, but maybe you understand this, right? If you consider path, space of path, then you have to have this. And so therefore, this part is a loop in the path space. Loop in this P of L0, L1. So therefore, the end point is not the same as the original P tilde plus, but maybe different things. And what we have is this. So maybe I denote this maybe U infinity, and then this dimension of the moduli space, P tilde minus and P tilde prime plus, plus prime. Yeah, this is certainly equal to mu of P tilde plus prime minus mu P tilde minus 1. But how they are related to these original things? And then I have just a computation like this. Originally, we have this, right? But after removing this sphere part, I get this one. And the difference is actually obtained by this. Okay. So now I can tell you this a little bit more. Yeah, computation. Okay. So now I also put one mark point in the interior. So I have this Ym P tilde minus and P tilde plus prime. And then I put one mark point, but this one mark point from interior. Because I have an interior point here, right? And this one is equal to mu of P tilde plus prime minus mu of P tilde minus plus 2 minus 1, right? So this has two-dimensional freedom. I don't know where it is. But this one is a one dimension coming from the group shifting trajectories. So I have these two things. So if you consider the modular space, this M1 sphere A, then I have a map to X, just taking value at this point, right? So here you have U, W, say, I don't know how, W, and then map to this W over this point star, because star is one of the data here. Right? Another one is also here, M1 of P tilde minus P tilde plus prime going to here, right? So this is all the same thing. So we have may U, and then U is mapped to, say, U of something. I don't know, so this one may be something, okay? So I mean this point is something, and this point is this star, right? And this is 2n dimensional. And this thing I wrote here, just dimension is 2n plus C1tx a minus 4. This is the dimension of this guy. And dimension of this guy is this, right? So the dimension of this one is this. So we have this and this. And if you just look at this term, so this one is equal to this mu of P tilde plus minus mu of P tilde minus. Okay. And here, the dimension is minus 3, right? Okay. So total space 2n dimensional. And if they want to meet, then this sum of the dimension must be bigger than 2n, or must be bigger than or equal to 2n. But let's suppose that this one is at most 2. Assume that this one is bounded by 2. And then this is up to at most 2, and this is minus 3. And so therefore, the dimension of the sum of dimension is less than the dimension of ambient space. So therefore, if you achieve some transversality argument again, then you can avoid this, right? So therefore, sphere bubble is not really a problem. To achieve transversality, sometimes you have to use this part of the theory, but somehow it is okay. But for this case, so this case is a problem. Maybe I have some time, or maybe I can have maybe 10 minutes or something, just to do some computation, and then I just finish this. So I think you can just do this sort of computation by yourself, and then you can see what is the problem. Okay, so now I have this thing, and then here's this P minus and P plus. And now I have a disk bubble here, so therefore maybe I start from P tilde minus, P tilde minus and P tilde plus. And in the end, maybe it may end up with this P tilde minus and P tilde plus prime with some this thing. It doesn't matter, this one is either side, yeah? So now I take this class beta. In this case, beta is in this H2 of x of L, maybe in this Li. Okay. And okay, so I do the same thing. So now I think of it as a union, is a configuration of this thing, so that I have one mark point here, and I have one mark point on the boundary, and then they meet, right? So we can also show that in the limit, the flow trajectory and disk bubble must be attached. Maybe it may be configuration of disk or something, but anyway, they must meet. And then I just consider moduli space of disk. So from now on, maybe for disk, maybe I don't really put disk as there. I mean, there I just indicate a sphere, but I often use disk, so therefore I don't really put disk here. And then I consider 1, but this 1 is now on the boundary, okay? Boundary mark point. And then consider this beta, okay? So this is the moduli space of disk with boundary, and then one mark point on the boundary, and map into this XL. So point can move anywhere on L, and so this one may be W here, and this is J holomorphic. And if you consider the image of this fundamental class, this is equal to beta. Okay, you consider such a thing. And then again, we mod out by the automorphism of the disk. PSL2R. And the dimension of this one is now equal to n plus so-called Maslov index of the Lagrangian along this beta plus 1 minus 3. Okay, so this is a dimension formula for this. And now I also consider this one. So in this case, actually, this one is, as I wrote there, this one is actually interior mark point, right, in this case. But now I consider boundary mark points. So therefore, I have to write this M1, but this one is now boundary of this P tilde minus and P tilde plus prime. And this is equal to mu of P tilde plus prime minus mu of P tilde minus plus 1 minus 1, right? Because this plus 1 is just boundary mark points. And minus 1 is the automorphism acting on the domain as a shift. So we have this and this. So I want to consider a similar thing here. So this one is the case previously we discussed. And now I consider the different case. Namely, here I have this M of 1 beta mapping to L, and M of 1, but this 1 is boundary map point of P tilde minus and P tilde plus prime to here. And this is n dimension. Okay? And one more thing is that here, actually, I wrote something somewhere. Yeah, this one is equal to this. I wrote this. And here, actually, this mu of P tilde plus minus mu of P tilde minus is equal to mu of P tilde plus prime minus mu of P tilde minus plus this Maslov index of these things. Okay, so just in this case, actually here we have a Chern number, but here it's actually Maslov index. Okay, and then just to do the similar thing. So here the dimension is I already wrote somewhere, just n plus mu beta minus 2. Okay, and this one has dimension. I just wrote it there. So this one is actually mu of P tilde plus prime minus mu of P tilde minus. Yeah? Because this is actually cancelled out. So we have these two things. And this thing is equal to this, right? So when we want to consider the Floer complex, as in the case of most case, we consider two critical points of index difference 2, and then look at the boundary of the modular space. So therefore, we may have to consider the case like this, right? But then here I have 2, here I have 2. So if it is equal to 2, then it is exactly dimension n. So here actually the dimension add up to 2n minus 1 at most. But here actually dimension sum up to exactly n. So therefore, this sort of argument cannot be extended to this case. And so what Yonghyun said is the following. So let's suppose that this one is at most 3. Okay? But let's suppose that this one is a massive index of the holomorphic disk. And monotonicity, as I wrote last time, is this mu of L beta is equal to kappa. And kappa is positive constant of these things, right? So omega over this beta. But now we consider only holomorphic curves. So therefore, this one represented by holomorphic curve, so therefore it's also positive. Okay? So that means this must be positive. On the other hand, we also assume minimal Maslov number is at least 3. So this number must be positive, and then it must be a positive multiple of 3. So this must be the positive multiple of 3, right? So therefore it is at least 3. So this one is at least 3, and this one is, sorry. I assume this is 2, sorry. This is 2, sorry. This is very bad. So this is at most 2, and this is at least 3. Then this must be at most -1, so negative number. So therefore, if you attribute transversality, then you can just avoid such kind of possibility. So therefore, you can actually, you don't have such contribution. So this is Yonghyun's argument sometime 93 or something. And then 94, actually, what he said is that if these two Lagrangians are Hamiltonian deformation each other, and then even though the Maslov number is 2, he can define Floer theory. So maybe I stop here, but the point is the following. Up to now, I discussed the case like this, right? Like this. So I consider some moduli space of Floer trajectories of index difference 2. And then look at the boundaries, and then you have two configuration of broken trajectories. And from here, we may say delta square is equal to 0. And such argument can be extended to the case monotone Lagrangian manifold, minimal number at least 3. So in the case of Maslov index 2, it may happen the following. So you have this sort of trajectory converging to this. But you may have different kind of end. So different kind of end. That is, so this one is this one. So this is a case like this, right? So this one corresponds to this. And this one corresponds to this thing. This sort of configuration may happen. So then, if you look at this picture, then probably you may think that no way to really get delta square is equal to 0. But there may be a chance to have a similar picture somewhere, so that these two things cancel out. And in fact, you have two Lagrangians, and these are the disks. These are disks with boundary on one side, right? But if you have the same effect from the other side, then they can be canceled out. And so, in fact, if they are Hamiltonian isotopic and assume that monotonicity, and then he could say that if you have configuration like this, then you can also have configuration like this. So they cancel out, at least modulo 2. And so he actually did it. And so this is actually the good point. And so maybe I will speak about so-called potential functions. And this potential function is somehow the kind of extension, generalization of such kind of ideas. And so in the case of toric Lagrange torus fibers of toric manifold, actually the Floer theory is actually controlled by the so-called potential function. And potential function is somehow counting disks on some part. So this is really the Yongen's observation 94. And I may come back to this later. Okay, thank you very much.